When we talk about digital trust, we're really talking about a few simple building blocks that everything else depends on. Hash functions give any piece of data a unique-looking fingerprint, so we can quickly detect if even a single bit has changed. Digital signatures use math to prove who created a message, and that it hasn't been tampered with. They're the cryptographic equivalent of a signed, sealed document. Key pairs introduce identity, a public key that you can safely share, and a private key that must stay protected. Together, they enable encryption and strong authentication at internet scale. All of this only works if the keys and random values are truly unpredictable. That's where entropy and randomness come in. They make it infeasible for attackers to guess or recreate our secrets. These four primitives are the foundation on which PKI, certificates, and modern zero-trust architectures are built. Hash functions are like digital fingerprint machines. You feed in any data, an email, a file, even a whole database, and they always produce a fixed-size string that represents that data. If the input stays the same, the fingerprint is always the same. Change even a single bit, and the output changes dramatically, which makes tampering easy to detect. They're designed to be fast to compute, but practically impossible to reverse. From the fingerprint, you cannot reconstruct the original data. They're also built so that two different inputs should almost never end up with the same fingerprint. In PKI, this property lets us sign compact hashes instead of entire documents, and be confident that if the hash matches, the underlying data hasn't been altered. To understand why modern hash functions are so powerful, focus on what's called the avalanche effect. If you take a message and compute its hash, then change just a single character, or even a single bit, a good hash function will produce a completely different output that looks random and unrelated. There should be no simple pattern linking the two hashes, even though the original messages are almost identical. This is what lets us detect tampering with high confidence. If an attacker alters a document, a certificate, or a software binary by even one bit, its hash value changes drastically. Systems can then verify integrity just by comparing expected and actual hashes, without reading or understanding the entire content. Modern algorithms like SHA-2 and SHA-3 have a very strong avalanche effect and resist known attacks. Older algorithms such as MD5 or SHA-1 are considered broken because attackers can create different inputs that share the same hash. Once that happens, the promise that any change is detectable no longer holds, and trust in the system collapses. Hashes are one of the quiet workhorses of PKI. They take any input and turn it into a fixed-size fingerprint, and that simple idea is reused everywhere. When we create digital signatures, we hash the data first, then sign that tiny hash instead of the whole document. That keeps signatures fast, while still binding the signature to the exact contents. Hashes also give us integrity verification. If even one bit in a certificate or file changes, its hash changes completely. Comparing the expected hash with the current one gives us mathematical proof that nothing was tampered with. For certificates themselves, hashes act as fingerprints. A short hash value identifies a specific certificate, so tools and logs can refer to it unambiguously. They also underpin revocation. Certificate revocation lists rely on hashed identifiers, so systems can efficiently check whether a certificate is no longer trusted. And in key derivation, specialized hash-based functions turn weaker secrets, like passwords, into stronger cryptographic keys, often adding salt and repetition to slow attackers down. Digital signatures are how we attach identity to data without trusting the network in between. Here's how it works. First, take the message and run it through a hash function to produce a short fingerprint. Then, Instead of encrypting the whole message with the private key, we only sign that fingerprint. The result is the digital signature, which travels together with the original message. On the receiving side, the recipient hashes the message they got. They also use the sender's public key to verify the signature and recover the fingerprint that was originally signed. If the fingerprint from the signature matches the freshly computed hash, two things are true. The message wasn't altered, and it must have been signed by whoever controls the corresponding private key. That combination, integrity plus a bound identity, is exactly why digital signatures are the backbone of PKI, certificates, and ultimately trust on the internet. In PKI, we almost never sign an entire document. We sign its hash. There are two big reasons. First is efficiency. A document could be gigabytes in size. Running an asymmetric operation over that much data would be painfully slow and expensive, especially on busy servers or small devices. A hash function shrinks that huge document down to a short, fixed-size fingerprint. Signing that tiny fingerprint is fast, cheap, and easy to scale. The second reason is security. Good hash functions are one-way and extremely sensitive to change. If someone alters even a single bit in the original data, the hash changes completely. When the signature is checked, the new hash won't match the signed hash, and verification fails immediately. At the same time, the signature itself doesn't reveal the original content, because you can't reverse the hash to get the data back. By signing hashes instead of whole documents, PKI gets both performance and strong tamper detection, which is exactly what modern digital systems need. In PKI, digital signatures are what actually hold the chain of trust together. Each certificate is basically a promise. A certificate authority is saying, I checked this identity and I stand behind this public key. That promise is encoded as a digital signature made with the CA's private key. When a root signs an intermediate and the intermediate signs your server certificate, it creates a chain of promises. Your browser or application walks that chain, and at every step, verifies the signature using the issuer's public key. If the signature checks out, you know two things. The certificate really came from that CAA, and its contents haven't been tampered with. If any signature fails, the whole chain is broken, and trust stops right there. So the power of PKI is not just in keys and certificates, but in these verifiable promises that anyone can independently check without talking to the CA again. Asymmetric cryptography is built around a simple idea. You have one key you guard like a secret, and one key you're happy to broadcast to the world. The private key is your secret. Anything done with it is assumed to be you. You use it to decrypt data that others sent you securely, and to create digital signatures that prove your identity or your approval. If this key is ever exposed, your identity and your encrypted data are effectively compromised. The public key is like a megaphone. You share it with anyone. Others use it to encrypt messages that only your private key can decrypt, and to verify that a signature was really created with your private key. Modern systems mostly use RSA or ECC for these key pairs. RSA keys tend to be larger. ECC can provide similar security with much smaller, more efficient keys, which is why it's popular in mobile, IoT, and high-scale environments. All of PKI builds on this pairing: a tightly protected private key and a widely distributed public key, working together to provide confidentiality and strong identity. Strong cryptography is only as good as the randomness behind its keys. The process starts with entropy collection. The system watches unpredictable events like hardware timing and user activity, and mixes that noise into an entropy pool. On its own, that noise is messy and uneven, but it's highly unpredictable, which is exactly what we want. Next, that entropy seeds a cryptographic pseudo-random number generator. This is a deterministic algorithm which, once seeded with enough high-quality entropy, can produce a very long stream of bits that are practically impossible to predict, even if you know the algorithm. Those random bits are then turned into actual keys. For RSA, they're used to find large prime numbers. For elliptic curve systems, they select secure curve points. If the randomness is weak or biased, attackers can sometimes reconstruct the private key, even without direct access to it. That's why serious environments use vetted tools, and often push key generation into hardware security modules. HSMs not only generate keys with strong entropy, they also keep the private material inside tamper-resistant hardware, which is crucial for the overall trust in your PKI. By now you know that asymmetric cryptography underpins PKI. So let's compare the two main families you'll see in real systems, RSA and ECC. RSA is the veteran. Its security comes from how hard it is to factor very large prime numbers. It's been around for decades, is very well studied, and almost every platform supports it. The trade-off is that it needs very large key sizes to stay secure, which makes operations slower and more power-hungry, especially at high scale or on constrained devices. ECC, elliptic curve cryptography, is the challenger. Here, security comes from a different hard problem, the discrete logarithm on points of an elliptic curve. For the same security level, ACID uses much smaller keys and is generally faster and more efficient. That's a big win for cloud scale, mobile, and IoT. The downsides are that the math is more complex and the ecosystem is newer, so implementation mistakes can matter more. For modern PKI designs, the industry direction is clear. Prefer ECC for new systems, while continuing to support RSA where you have legacy constraints or compatibility requirements. When we talk about entropy in cryptography, we're really talking about how much true unpredictability we can feed into key generation. There are two big ideas here. First, most systems use pseudo-random number generators. These are algorithms. If you know the starting seed, you can reproduce every random value they output. That's acceptable only if the seed itself is impossible to guess. Second, you get that unpredictable seed from real-world noise. Hardware random number generators. Tiny variations in mouse movement, keyboard timing, or network jitter. The operating system constantly collects this noise into an entropy pool. Every cryptographic key you generate ultimately depends on how strong that pool is. If the entropy is weak or predictable, an attacker can dramatically reduce the search space and recover keys. If the entropy is high quality, even a powerful attacker has no practical way to guess or replay your secrets. Up to now, we've treated randomness as a building block. Here's what happens when that block breaks. When the Debian OpenSSL bug removed a key source of entropy, systems still worked, but they produced keys that were easy to predict. That meant attackers could quietly decrypt traffic and impersonate legitimate servers and users at internet scale. The same pattern shows up with weak TLS nonces. A nonce is supposed to be a unique one-time random value. If it repeats, certain signature schemes leak enough information for an attacker to recover the private key itself. One bad random number can permanently destroy the secrecy of a key pair. In IoT, devices often boot before the system has collected enough entropy. They all generate random keys that are actually very similar, or even identical. Now, compromising one device can give you a shortcut to compromising thousands. The lesson is simple. Keys, certificates, and protocols can be mathematically perfect. But if your randomness is weak, your entire PKI is weak. Always treat entropy sources, PRNG configuration, and startup conditions as first-class security controls, not implementation details. Now that you know the individual steps, let's connect them into one lifecycle story. It starts when a system generates a key pair. The private key stays secret. The public key will be shared. Using that public key and some identity details, the system builds a certificate signing request, or CSR. The CSR is then signed locally with the private key, so the certificate authority can be sure that whoever is asking actually controls that key. The CA receives the CSR and performs its own checks. Depending on the assurance level, that could mean validating a domain, an organization, or even legal documents. If everything looks good, the KEA uses its own private key to issue and sign a certificate that binds the subject's identity to their public key. From that point on, any client connecting to this service can verify the certificate using the CA's public key, then run the usual protocol checks, like hostname matching and revocation status. If those checks pass, the client can trust that it's talking to the right entity and can safely establish an encrypted connection. To see how PKI actually works, it helps to zoom in on 4 basic building blocks. First, hash functions, fingerprint machines for data. They take any input and produce a fixed size output that's deterministic and one-way. If the hash changes, you know the data changed, which is why hashes are central to integrity checks and signatures. Second, digital signatures. These combine hashing with private keys. You hash the data, then sign that hash using a private key. Anyone with the corresponding public key can verify that signatures. That proves who signed it, that the content wasn't altered, and gives you non-repudiation. Third, key pairs. PKE relies on take-it, a private key that must stay secret, and a public key you can share widely. With this pair, you can encrypt in one direction and decrypt with the other, or sign with the private key and verify with the public key. Modern systems often prefer ECC algorithms for efficiency and security. Finally, entropy. This is the randomness you use to generate keys and other secrets. If your entropy source is weak or predictable, everything built on top of it is fragile, no matter how strong the algorithm looks on paper. Good randomness is the invisible foundation of all cryptographic security. Before we move on, take a moment to connect these cryptography ideas to your own environment. First, think about how your organization generates keys today. Are there clear standards for which algorithms you use, like RSA versus ECC, and what key sizes are allowed? Is key generation centralized, or does every team do it differently? Next, consider randomness. Where does your critical infrastructure actually get its entropy from? Hardware modules, operating system sources, cloud services. And more importantly, who has ever validated that this randomness is strong enough and properly configured? Finally, pick one concrete system you know well. It might be a production API, a mobile app, your CI pipeline, or an internal admin portal. Identify exactly where it depends on digital signatures for trust. Maybe code signing, TLS certificates, or signed emails. As we move deeper into PKI, keep that system in mind and ask yourself, if the keys, randomness, or signatures here failed, what would the real impact be?